Okay, so good morning, good afternoon, good evening. This is a recorded lecture. I do not remind anything about the previous chapter because it's a new one. There will be a summary on the website about the previous chapter. So now it's chapter 5 because we want to deal with cooperative games. So far the players were independent. Now they can interact. But of course, I need to introduce the framework. So we continue with games with n players. It's the same as before. And they are denoted by 1 up to n on the set of n players is denoted by capital N. But we would say that coalitions, so groups, are possible. So we need to represent what is a coalition, or what is a coalition, or what is such a group of players who are going to share or to play together. So they are possible, and they are going to be represented by simply subsets of n. So among the n players, some can play together, and with that, it's going to be a subset of these n players. And the number of players in one coalition is going to be denoted by S with this number. This is a number of players in this coalition or this group of player S. Okay. So it means this number of players can be, in fact, it can be 0. I will explain 1, 2, and we can have up to n players in one coalition. And if this number is 0, it means that S is the empty set. If you have nobody in a group, the number of players in this group is 0. And if you take S equal to capital N, so if this group contains all players, we say that S is, there is only one, and it's called the grand coalition. So it's probably from French, grand coalition, which means a big one. And probably you remember all subsets of n, they can be represented. There is a notation for the set of all subsets of n. They can be represented by 2 power n. This is a notation which means all subsets of the set n. So let me just give you an example. If we have 4 players, 1, 2, 3, or 5, one possible subset would be 1 and 3. 1 and 3 could be a possible subset, or we could have 3 to 4, which is a possible subset. For now, I'm not claiming that they are disjoint. Or we can have a subset with everybody. This is also a possible subset. This is a grand coalition. So it means we can represent group of players by subset of these n players. Okay, so what is the first section in this new chapter? It's what is called non-transferable utility games. But They are usually, so this is a long title, non-transferable utility games. They are usually just denoted by NTU games. Okay. And we will see it means, this is essentially the most general framework, but it means player can play together, but they cannot share the payoff. So each player is going to have a certain payoff, we will see, but they cannot share what they get. One player cannot give to another one. Let me write something about this. So these NTU games, it's a very general family. In fact, it's even too general. We will see subset later. So it's a very general family of games, of cooperative game. But it's called not non-transferable because there is no direct transfer of payoff between players. It's not very precise. In fact, okay, this is a general idea, but we have to be more precise. I need to introduce one concept or one thing. You all know the vector space Rn. So you all know the vector space Rn. I need to define something which is, you will see, it's very much related to this, but it's a bit more precise. So I first define vector of R for, if it doesn't tell you anything, it doesn't matter. We will see many examples and you will understand. This is a set of all real vector space of finite dimension. Don't worry about this notion, but I need this for, just to be precise. And for example, so of course, Rn, but what is Rn? This is a set of x1, x2, up to xn. It's a vector with all xj real numbers. So this is Rn. And this is an element. This is a real vector space, so it's an element of this set of all vector spaces, real vector space. But 0, just the point 0, is also an element of, this is a very special one. It's of dimension 0. But now I need to define a new real vector spaces. So for any subset of n, and I will take an example in a second, I'm going to define Rs. What is R with, as an exponent, a subset of n? It is a set of xi, xj up to xk, on its own purpose that I don't write numbers, such that, let me take some space, such that these are all real numbers, so xi, xj, xk are real numbers, but ijk are element of S. So let me take an example because it's very simple, but Yeah, now, you probably haven't seen this notation so far. So for example, if I take R, let's say N is, let's say 5. So it means we have 5 players. But I take the subset S, let's say 1 to 5. So I'm going to define R with a set 1 to 5 simply as a set of x1, x2, x5 with x1, x2, and x5, all real numbers. So what is important, and it plays a role, the name of these variables is associated with this subset of N. So it means, be careful, for example, this space is not the same as R with power 1, 2, and 4. Of course, these are both are 3-dimensional vector space, so both of them, so this one and this one, they belong to my vector space vect R. But this one uses the coordinates 1 to 5, while the second one uses the coordinates 1 to 4. And it's important just to take this into account. The coordinates are indexed by a subset of S, a subset S of N. And why we have to be careful? Because, as I said, these two real vector spaces are not the same, but it means R 1 to 5, it's not the same, so be careful if you are familiar with subspace. It's not the same as the set x1, x2, 0, 0, x5, so that x1, x2, and x5 belong to R. This is naturally a subspace of R5, but it's not the same. Here, I'm giving the value 0 and 0 to x3 and x4. But in this one, and it's important to realize it, x3 and x4 simply do not exist. It's a 3-dimensional space, that's it, and it's made of the variable 1, 2, and 5. Nothing very complicated, but you probably have not seen this notation before. And all our real vector space, you just take care of which variables are involved, and the variables are indicated by this S, which is a subset of N. Okay. I hope you have no question. If you have any question, you ask a colleague or you can ask me later. Now, so it means I'm going to play with subset of N, so some variables inside N, and I'm going to consider 2 points, x, y, in Rs. So it's a vector space. Oh, I should have mentioned this is of dimension. So this vector space is of dimension, of course, the number of element of S, because this is a number of variables. So for x and y in this subspace, we are going to put an order. We say x is smaller or equal to y. Be careful, we are dealing with vectors, so I need to give you the meaning, and it's not the lexicographic order which I mentioned quickly in one exercise. We say that x is this vector is smaller than 1. And by the way, this is the same as y bigger or equal to x. I will use the two notations. If xj is smaller or equal to yj for any j inside S. So it means you do a comparison entry-wise. So each entry of these two vectors, you compare them. But of course, they have variables only indexed by j. So you can, in my example here, you compare x1 with y1, you compare x2 with y2, and x5 with y5. And if you have this inequality for all of them, you say that x is smaller than y. Okay. So again, it's not the lexicographic order. And of course, I put a smaller or equal that you can put a strictly smaller. So you say x is strictly smaller than y, which is the same as y strictly bigger than x, if xj is strictly smaller than yj for all j in S. Okay, so we are going to compare x and y to vectors in some real vector space, just component-wise. And now there is a new notion, which probably you haven't seen. A subset A in this vector space, Rs, is called comprehensive. This is a word, it's called comprehensive if for any x, y inside Rs, yes, with x smaller or equal to y and y in this set A. So whenever you have a y in A on an x which is smaller, then x also belongs to A. So I encourage you to draw a picture. What means that a set is comprehensive? And you will see that these sets are infinite. They are very big, but they have a certain direction. Let's do the example with the simplest example. If I take R1, which is just the set of x, set of x1 for x1 real. So this is just a vector space of dimension 1. What is a set which is comprehensive? This is the simplest case. A is comprehensive if A has a very specific form. It's of the form minus infinity up to a certain number A. And it doesn't matter here if it is closed or open at this point. So you see it satisfies the y, the biggest y is this one, and all points which are smaller have to be inside. So this is a comprehensive set in this one-dimensional vector space. I'll let you do a picture for 2-dimension or 3-dimension. But it can be more complicated than this, but they have to go to infinity in a certain direction. And now if you take for A inside Rs arbitrary, so you take, let's say in R2, you take an arbitrary set A, you can construct the smallest comprehensive set which contains A. So the smallest comprehensive set containing A is called, this is a general notion, the hull, or the comprehensive hull. That's the comprehensive hull. The comprehensive hull of A. And it's denoted, I'm not sure I will use this notation, but is denoted by hull of A. Again, I let you draw some pictures. So you take this A, for example, and you can see what means the comprehensive hull. It's not difficult. Okay. So we have seen what, so far we have seen what means RS for S, any subset of n players. I introduce an order between elements of RS, and we have defined this notion of comprehensive, which it means whenever one point is, so a comprehensive set is whenever you have one point y in A, all the elements which are smaller, in the sense introduced here, are also in A. And so if you take an arbitrary set, you can construct the comprehensive hull. Okay. You cannot ask any question, but please think about this. And heavy do, please ask next time. I miss your questions. Okay, so in the notes, I encourage you to draw one set on one comprehensive hull. Okay, so now I can define what is an NTU game. So non-transferable game. But as I said, it's very general, so very soon we will go to a smaller family. So, non-transferable, non-transferable utility game. Or simply NTU game. It's in fact only two things. Is a pair. It's rather simple. It's a pair NV. And you already know N. With N is our set of N players. Okay, but V, of course, it's a bit more complicated. And V, it associates. It's a function, but it's a bit complicated. To any subset S of N, so it associates to any S inside N, a subset of which it's called VS, is VS of RS. If you try to write it as a function in the sense the function I introduced in calculus, you will see it's a bit complicated because the image, or more precisely, this VS, which is a subset, is in a space which depends on S. So if you try to write it as a function, it's not easy. That's why I'm a little bit, no, it's precise, but I do it with words. V associate with any subset of the set of N players, a subset of RS. For example, if this would be a subset of R, let's say 1, 2. If we are dealing with a variable 1, 2, this would be a V of the subset 1, 2. Okay, this is a subset. But of course, I need to impose a few more conditions. So that's not enough. So we impose a few things on this V. Such that first, V of the empty set, because remember, the empty set is a subset of N. It's no player. This is just the point 0, because it has to be in the set the empty set, which is, as I mentioned before, this is just the point 0. So it's the only point in this. Now, this is quite natural. Don't worry about this. But now, and we have addition conditions. V of a subset containing just one player, V of I, it has a specific form. It is a set of xi belonging to R, so that, so that xi is smaller or equal to a certain number vi, which means it is exactly what I mentioned before. It's an interval of this type for some vi natural number. So it means the special set associated with a subset of S which contain only one element has exactly this form. Okay. And one more condition. For any other S in N, S not the empty set, Vs is non-empty. I don't want to have the empty set, is a non-empty closed remember, closed means it contains its boundary. So it's a non-empty, closed, and comprehensive. So now I'm sure you have done some pictures, so you know what it means. Some comprehensive VS is a non-empty, closed, and comprehensive subset of RS, with one more final condition. V of S intersection the set of X in RS, so that XI is bigger or equal to VI. Is bounded. I will give you just now an example. Okay, so let's summarize. NTU game is something rather simple. It's two things: the set of n players, a function v, which take any s in n and associate a subset of this vector space Rs with a few conditions. First, the empty set is sent to 0, but you have no other choice. This is more, no, this, in fact, it's the only, this half interval or half line is, as I already mentioned, it's the only one which is comprehensive in one dimension. So if you want all V of S to be comprehensive when you have only one dimension, this is the only solution. So it says that V of one player is this set for some Vi in R. And now for all S which are not empty, we assume that Vs, so in part, it holds also for this one. We assume that Vs is non-empty, closed, this one is closed, comprehensive subset of Rs, plus one condition. the fact that this set intersection, or when you intersect all xi bigger than this vi, this is bounded. So let's look at an example. And as I have written in the note, there is an interpretation for this example. I don't want to introduce it during the lecture, but in the notes you can find more information. But let me just give you this example without any interpretation for now. So an example is, I take n is equal to 3, so it means the set of all players is 1 to 3. Of course, V of empty set is just 0. Now, V of I for one player, as we have seen, it is minus infinity, and I fix 0. I mean, it's an example, so I fix 0 for the VI. Now I need to say with two players, so V of 1, 2. 1, 2 is a subset of 1, 2, 3. I'm going to choose the set of the x1, x2, because it's in two variables. The variables are x1 and x2, such that x1 plus 4x2 is equal to, or is smaller or equal to 1,000. And, there is a second condition, and x1 is itself smaller or equal to 1,000. You will see, if you look at the example, you will see why we have these numbers. So I define V of 1, 2. I need to define V of 1, 3. This is a set of x1, x3, so that x1 is smaller or equal to 0, x3 is smaller or equal to 0. Yes, I need to define V of x1, 2, 3. And I do something similar. It's a set of x2, x3, so that x2 smaller than 0, x3 smaller than 0. And finally, I need to define V of 1 to 3. It is a set of vector with 3 variables, x1, x2, x3, so that x1 plus x2 plus x3 is smaller or equal to 1,000. Okay. So you can represent these sets as the first one, it's just an interval for the corresponding variable. V of x1, 3, it has to be smaller than 0 for both variables, so it's something like this, and the same for 2, 3, but with different variables. I encourage you to represent this, what subset it is. And you can, this is easy, it's also in 2 dimensions. It's a subset with 2 conditions. So x1 is smaller than 1,000, and you can represent this condition. And you can check, so this is an example, but now I just define V. You need to check that all these sets are closed. It's quite easy to see that it contains their boundary. You have to check that they are comprehensive. But here, for example, it's easy. Take any point. The ones which are smaller are like this. These are the points which are smaller. So it's inside. They are comprehensive, closed, non-empty. None of them is empty. And you need to check this condition, the last condition. So you take these sets and you check Vi, we can see there it's 0. you can check that the intersection with x1 bigger than 0, x2 bigger than 0, or x3 bigger than 0 give you a bounded set. So it's inside a box. You can put it in a box. So with this example, you can check, oh, this V satisfies the condition of an NTU game. And again, the interpretation is given in the notes, and I took it from the reference book. Okay, so that's a definition. What is an NTU game? Let me write a few remarks. The first one is that some authors they impose that Vs or require V of S to be convex. In my definition, I don't assume it. If necessary, we can assume it later. And the second remark, they exist. I'm not the most abstract guy in the sense that there exists more abstract definition. My definition is very concrete. We are dealing with subset or subspace of Rn or subset of real vector spaces, but there exists a definition, an abstract definition of NTU games, which is more complicated, but essentially equivalent, more complicated, but essentially equivalent. In fact, I look at one more complicated one, and when you put all the conditions, you end up with something which is of this type. So you don't get very much by looking at a more abstract one. Maybe you can find one, but I'm not sure it's really useful. Okay. And a last remark, I'm sure you already observe it. What is R power n? Take the biggest one. I'm sure you have observed that this is only your usual space Rn because you take all variables. So you have the variables from x1 up to xn. And the elements of Rn, so the points in this space, are usually called, in this framework, they are called allocations. They are called allocations. And represent, usually they represent what a player what the players can get from the game. So yeah, I mean, this is what so far we call the payoff. So these numbers correspond to the payoff. I suspect that sometimes it's slightly different from the payoff, but in most applications, the points in Rn are what the players can get, so this is a payoff. And in fact, in the abstract version of this definition, you do one more step, you define one more space, and then the utility function is defined on this space, but it takes value in R, so you end up in Rn, so we are almost equivalent. Okay, so if the remark is we haven't assumed convex, but it might be, then there exists an abstract version of this definition, but I stick to this one and observe that Rn, capital N, so the grand coalition is the same as Rn, and these points are called allocation. This is just a word. Okay. Now, the next definition, you need to think about it for a second. It's not difficult, but it's not completely trivial. So let NV be a NTU game. An allocation, so point, I remind you, it's a point in Rn is a feasible, this is the word, feasible allocation. I define what is this. If there exists, so be careful, there exists a party, oh, I use a notation. There exists a partition which I'm going to write S1. I use this notation S2 up to SK of S, of N. So it means you subdivide N into K subset and they don't intersect. So it's a partition of N. And for each, allocation, I should give a name. This allocation, I call it X. So this point in Rn, this allocation, I call it X, is a feasible allocation if there exists a partition and for each of these sets, or for each L belonging to the set 1, 2, up to K, there exists a Y inside RSL with Y index I is equal to XI, or any I. So it looks complicated, but it's not so complicated. So remember, we have our N players. So a point X is in Rn. So it has N components. Or I should write R, it's the same, but I should write R capital N. But of course, this is R. It has N components. Now we have the set 1, 2, 3, up to N. And I'm going to say that this point is feasible if I can subdivide, let's say, this set into 3 parts. Okay. So it means in my example here, L is 3, K is 3. K is 3. It's a partition of these endpoints. And so in the yellow one, in R, so if I'm very precise, in R 1, 2, 4. We have a y in R. So I will call, okay, in R3, 5, we have another vector which I'm going to call, in my definition, I use this, okay, let's see, these are different points, and in R6 up to N, we have a different y. And what is the condition is that here, this vector is equal to x1, x2, x4. This one is equal to x3, x5. And this one is equal to x6 up to xn. So x is one point with n variables. I call it feasible if I can subdivide. No, sorry, there is a small mistake. The y is not in R. Sorry, this is not correct. There would always be one. This would be too easy. You just take the same. So there is a mistake here. It's in V of SL. So this y, of course, it is in this space, but it has to be more precise. It has to be in V of 1, 2, 4, which is a subset of indeed R 1 to 4. This one is in V of 3, 5. And this one is in V of the set X up to N. So you should come back to the example which was before on the blackboard and see what it means. Not all points are feasible. It means each coordinate has to be precisely in one of these subsets. And if it is satisfied, then it's called feasible. It means X is, a point is feasible if when you look at its different coordinates, some of them can be put in one V of the corresponding S. These are some S, S1, S2, S3, and you have this equality. So I encourage you to think about this definition. It's not difficult, but take an example, use the example I mentioned before, and you will see not all points are feasible. It really depends on this function V. So I'm not even sure that, yeah, probably there is always some feasible points, but the number is not clear. So I told you, this definition is not so difficult, but it's not trivial because you take a partition of N and you have to satisfy what is written there. And as I meant, as it is visible, I use in this line the same y, because otherwise it would be complicated. But be careful, it means we have 3 different y in this example. Why I don't want to be more precise, because if I write a y index L, because it's in V of SL, it's confusing. So I don't want, so maybe I should put a power L because it's not the component. So maybe this would be the good y with the exponent L. So we would have this with a L, and this would be the first, let's say this is S1, this red guy is S2, and the white one is S3. Then this would be y power 1. It's not the index. This would be y power 2, and this would be y power 3. But I'm not sure it helps. Okay, so we know what is a feasible allocation. In a sense, it's one way to put the players in different groups such that this point has a natural relation with V. And now I have one more paragraph, and then we are going to go to a much simpler framework. So what is the next step here? Then we look for rules for finding good, whatever it means, good feasible allocations. So for now, I gave you only a general definition of these feasible one, but probably we want to put some rules which select one solution or one special one. So it's called, in this framework, a solution is a set of rules. We will see very concretely what I mean by this. It's a set of rules for choosing a feasible allocation according to or respecting some prescribed conditions. So we will see in a second. Prescribed. Oh, I'm not sure how it's written. Or some given condition. Some given conditions. Okay. And this is a called solution, but it's also called, and I will come back, it's called allocation rule. Allocation. So we will provide some allocations rule. But as you can guess, in this very general framework, it's a bit abstract and complicated. So we will now look at one example, or one family or one subfamily where it's easier. And next time we will look at something slightly more involved. But it's always the same idea. We are going to put together some players in order to get something. And this something is not defined yet. So, sometimes we need to collaborate in order to get something that you cannot get if you don't collaborate. And up to today, we have not seen any framework for collaborations, but precisely this framework is for collaborating. And any subset of N is going to represent a collaboration. Okay, so 5.2 about bargains. As I said, this is a rather simple subset in what I will introduce. So the idea is here players, they look for a feasible allocation. They look for one satisfying, and otherwise, if they don't get it, if they cannot get a feasible one, they get what is called a disagreement allocation, which is fixed from the very beginning. So if they cannot get any feasible one, they get one which is prescribed. This is a kind of worst scenario. So I'm going to introduce this subfamily of games, but I just need one notation before, and we will check that it's indeed a subfamily. It's an exercise. So just a notation for any F inside Rn, and for a point D inside Rn, we set F index D is a set of X inside F which are bigger than D, in the sense I have introduced before. So it means each component, this is a vector, it has n components. It's a vector, it has n components. And I look at each component, and each component xi has to be bigger than the component di. So this is this notion of fd. D is going to be the disagreement point I mentioned. So we are looking for some, you can guess, as I said, the disagreement point is going to be the worst scenario. So we will look for something which is bigger than D. So it means for each player, it's bigger than the component Di corresponding to player I. So this FD is quite natural. It's better than the disagreement point. Okay, so what is these bargains? N player bargaining problem. So I give a slightly different definition, but we will see that it fits with the previous framework. Is a pair. It's a pair FD with F any subset of Rn which is closed, convex, and comprehensive. Now, I'm sure you have done a few pictures, so you know what it means. And D is a point in F. So I take, in the previous definition, it was arbitrary, but now I take D in F, and it's called the disagreement point. Disagreement point. And F, I should have mentioned the name F is, this F is called the feasible set. So, and there is one more condition. But so it means the bargaining problem is just a subset of Rn, which is closed, convex, and comprehensive, a point D, which is inside F. And there is one more condition between these two things. So such that Fd, which I have introduced here, Fd is closed, which is not a big requirement, unbounded. And not reduced to D only. Why? Because it could, if you take F, all the points which are smaller than D, then Fd, because it's a set of points which are bigger, could be only D. But in the assumption, it means we assume that players can do better than just D, otherwise the game is over. Yeah. If you don't take this last assumption, you don't have anything to do. And still in the definition, now the set of all bargaining games so these are FD, is denoted by, it's a notation Bn. So Bn is made of pairs Fd satisfying what is above. So the set of all bargaining games, it's of course a huge set. It's an infinite set, but it's the set of all bargaining, I should say bargaining problem. Probably the same as bargaining game. Bargaining problem is a pair FD, F is convex, closed, and comprehensive subset of Rn, D a point, and such that this condition are satisfied. Okay. Now I said, oh, these are subfamilies of what I introduced in the previous section. So we need to check. The previous section objects were made of N and D. So I need to check that it's meaningful. So remark, define V by, so I need to define V of the subset N. I define it like this, the F, and I define V of S as the set of X in R. S with Xi smaller or equal to Di, any I belonging to S, for S, of course, different from N, but S inside N. And probably I need to define, because it's not automatic. Okay, so I give this definition. I define a V. And you can see V contains the information about F. So it's a V associating to this grand coalition F. And it contains the information about D, because Vs is a set of points which have components smaller than Di. So in my definition of the function V, I use the two information. And now there is an exercise you can do even if you are first year. Exercise, check that this NV, with the V I have just introduced, is a NTU game. So if you do this exercise, it means you have checked that with any bargaining problem, we can associate an NTU game. In this sense, these bargaining problems are part of the NTU games, but you can see already that they are quite simple. Why they are simple? Because, okay, this one is not trivial, it depends on F. Just, yes. But these ones are quite simple. You have only the information about Di, so all these sets look quite similar. So it means compared to the very general framework, this is a very specific subfamily of NTU game. So again, you can do this. You can check this easily, because you have to check the conditions on NTU games, but they are easily satisfied here. Okay. Now, let me just say, in this framework, probably for some historical reason, for X and Y belonging to F, we say that X is Pareto dominated. It's an Italian mathematician and even more. It's Pareto dominated by Y if X is smaller or equal to Y and X is not equal to. So there is nothing special. I mean, it's what I mentioned before, the order mentioned before, with the assumption that X is not Y. For some historical reason, it's called Pareto dominated. And still, and Y is, this is probably more important, it's Pareto optimal if there is no allocation. Yes, but remember, allocation is just a point. In an allocation, I will call it Z in F, which Pareto dominate Y. So we say that Y is Pareto optimal if you can dominate, you cannot, by assumption, by my construction, Y is in F. So we say that Y is Pareto optimal if there is nobody still in F which dominates Y. So there is nobody in F which is bigger than Y in the sense I mentioned. Okay, so nothing new except this name, Pareto dominated. It means this inequality or not an equality, and Pareto optimal means you cannot dominate by Y. Okay. Now, at the end of the previous section, I said now we look for rules for finding feasible allocations. But as I already mentioned, in this case, it's rather simple because the only very simple element is this Vn. So, but in the end of the previous section, I mentioned allocation rule. So an allocation rule for n-player bargaining problem I should write for all, no. Yes. For all bargaining, n-player bargaining problems, probably I should be more precise, is a map. It's a function phi. And why I corrected all players and players bargaining problems, because it takes any bargaining problem and send it to an element of Rn. So it means, oh, there is one more condition, so that, no, it's good. A bargaining problem is a pair FD. So it takes any FD and send it to, so this is a point in Rn, but I'm more precise, is here a point in Fd. Fd is a subset of F of all points which are bigger than D or better than D. So for any Fd inside this. So yes, I should be, maybe I will correct if necessary in the notes. Allocation rule is a function which takes any n-player bargaining problem. So any element, this is a set of all bargaining problems, n-player bargaining problems. So it takes any n-players bargaining problem, send it to Rn, but more precisely for the bargaining problem Fd, it sends it to a point inside this subset Fd. Remember, it's a set of points in F which are better than or bigger than D. Okay, this is an allocation rule. Then a natural question is, oh, this is very general. Can I impose some condition so that there exists only one allocation rule? So there would be only one function which send me to the best, or in a certain sense, to the best point in Fd. And indeed, there exists a list of 4 conditions, which will, the end of the story is I will impose 4 conditions, and then the statement is, oh yes, under these 4 natural conditions, there exists only one only one phi which satisfies these 4 properties. So let's list 4 properties, and we will see that they are quite natural, that phi should satisfy. So I'm going to it will take some time, but I'm going to list 4 properties, and then the final statement will be, under these 4 conditions, there exists only one phi which associates to any bargaining problem a solution. So the first one is related to Pareto condition. It's called the Pareto efficiency. So phi satisfies. So phi is a function from the set of all bargaining problems to Rn. Satisfies. This is called the EEF. I don't know exactly. Efficiency, probably. It satisfies the EEF condition. These letters are not from me. It's probably some classical names. So it satisfies the EEF condition if phi of Fd is Pareto efficient. Or in F, which is quite natural. If you think about it, we have a notion of optimality, or is it Pareto? Oh, probably, no, sorry, it's not correct in my note. It's Pareto optimal. I haven't defined what is Pareto efficient. So it's Pareto optimal. I have defined Pareto optimal. So it's Pareto. So phi, take any bargaining game, send it to a point in Fd, and we want it to be Pareto optimal, so there is not a better one. It still doesn't mean it's unique. No, there are many points which are Pareto optimal. So this is the first condition, which is quite natural. Okay. For the second one, I need to introduce some notion of symmetry. It's like when today we played with, on the last lecture, we played with, I said all players play the same strategy because we cannot distinguish them. There is something similar here. So first I introduce, let pi be any permutation of n elements. So you have probably seen already a permutation. You take n elements and you send them pi So for example, you set the first one to the third one, the third one to the second one to the first one, and let's say this is a number 2. So this is a permutation. Okay. So I just call pi any permutation of n elements, and I called x pi. It's going to be an element of Rd. Index I is, I give a definition, it is x of pi of I. So let's check. I permute, so for any x in Rn, I have n indices and I exchange them. So the x pi is a new vector, it's a new element. This is a new element of Rn. Its index I is obtained by taking the x of the pi I, which is a permutation. Okay, so this is a permutation of a variable. And now we say FD, so this bargaining problem is symmetric. This is a definition. We say that this bargaining problem is symmetric if the set F, if F is I will explain, is invariant under any permutation, and d pi is d. So it means d is also invariant under any permutation. So what means F is invariant under permutation? It means you look at the point x pi, this has to belong to F for any x in F. This is the notion of invariance. Take any point in F, apply this permutation, it has to be again in F. You can make a small picture what means invariant under permutation. You will see that the subset are, you have a notion of symmetry. Okay. So we say that bargaining problem is symmetric if the subset F is invariant under permutation and pi d is also invariant for any permutation. So of course, not all bargaining problems, there are plenty of them which are not symmetric, but among all bargaining problems, some are symmetric. And we say that this is a second condition, which is a condition of symmetry. Pi satisfies the SIM, this is quite SYM condition. You can guess why. If for any symmetric game, so we start with a symmetric game, symmetric bargaining problem. So if you start with a symmetric one, then pi of FD is equal to pi of F. Oh no, sorry. What does it mean? So you start with a game which has a certain symmetry on the, which has all symmetry under permutation, and you impose that phi should respect that the image of FD, a symmetric bargaining problem. This is a point in Rn. Take its component I, it has to be equal to its component j for any ion j in 1 up to n. So it means if you start with a symmetric game, the point you get is also symmetric, which is quite natural. Your phi should respect the symmetry. If your game or your bargaining problem is symmetric, then the outcome of the phi is also symmetric. Okay, for the next condition, I need to recall something. F, a function from Rn to Rn, this is n variable calculus, is, I add this word, diagonal, is a diagonal positive affine transformation. It's a positive affine transformation, which is also diagonal, if there exists a matrix A, Mn of R, which is diagonal. That's why I call it diagonal. So it means it's a matrix, it has just an entry on the diagonal, and that's it. Maybe I can give a name. Lambda 1 up to lambda n, because it's a diagonal matrix, with all lambda j bigger than 0. So the elements on the diagonal are bigger than 0. So there exists such a matrix, and a certain B, which is an element of Rn, such that f of x is nothing but ax plus b. Okay, so for any x in Rn, x. So I call a diagonal positive affine transformation of transformation, so from Rn to Rn, but which has a very specific form. It's a matrix applied to X plus a translation. And this matrix A is diagonal, and each entry on the diagonal is strictly positive. So it's very, very standard or very simple. It's not even a rotation. It's a scaling. You can think about this. You rescale each entry and you add a B. And it's called diagonal because this matrix is diagonal. It's called positive because all these guys are strictly positive, and affine is this relation. And we have already mentioned this affine transformation. If you come back to the very beginning, when we introduced the linear utility function, we had a result which said, oh, these utility functions are unique up to affine transformation. You can come back to section or chapter 1. And in fact, the next condition is precisely related to the fact that this linear utility function is not unique, but it's unique up to affine transformation. So the third condition, which is covariance, it's called covariance with diagonal positive affine transformation. Of course, I will write this only once. Covariance with diagonal positive transformation. So we say that phi satisfies the cat condition if for any f of the type, I don't want to write it again. So it's a type which is mentioned here, which is a diagonal positive affine transformation. If for any f of this type, one has phi of f of capital F, f of D is f of. Okay, what does it mean? The right-hand side is understandable. Phi of capital FD is a point in Rn. I apply this affine transformation. Now, what is the left-hand side? Here you apply f to D. Here you apply f to a set, which means you take any point in f and you apply small f. So you get a new set. So you have a new set here, a new set here, and you apply phi. By the way, you should check that this is, again, a bargaining problem, but I didn't check, but probably it's easy because f is very special. So you should check that if fd is a bargaining problem, small f applied to f and small f applied to d is, again, a bargaining problem. And the statement or the condition is that when you apply f, small f to this bargaining problem and then phi, it's the same as first applying phi and then f. And again, this is related with this invariance or uniqueness modulo affine transformation, which we have seen a long, long time ago. Okay, I want to continue for a few more minutes. Since it's a recorded version, recorded lecture, you can stop, take a break, relax, and come back. I'm free to make it a bit longer because it's also for 2 lectures. I want to finish this, it's not so long. I want to state the fourth condition and then the theorem. So probably it will take 10 more minutes. But I'm not cheating. You can take a break, and this is only 10 more minutes for the next lecture, or 15 minutes. Okay, so we have seen 3 conditions on phi, and so far they are quite natural. The first one, what was it? The first one, yes, is this Pareto efficiency. The second one is about symmetry. If a bargaining game is symmetric, the result by phi should be symmetric. Covariance, it's maybe less understandable, but it's related to the general theory. And the fourth one, the fourth condition, it's called independence of irrelevant alternatives. So we have to check what is the meaning. And apparently this condition is, people are not always happy with it. So we say that phi satisfies the II a condition if. So we have 2 bargaining games. If for any fd and a second f hat d, be careful, it's the same d, but it's a different set. Both are bargaining games, so they both belong to Bn, and we assume that f hat is a subset of f. So we have 2 bargaining games or 2 bargaining problems on the same disagreement point, but f hat is inside f. And we assume, of course, some compatibility between these two, so that if for any game satisfying this, and if phi of fd is inside, so this is a condition. You suppose this is a point in Rn, but you suppose that this point is in fact inside this one. You know that it should be in F, but you assume that it's inside this one. Then phi of F hat D has to be equal to phi of Fd. Okay, this is called the independence of irrelevant alternatives. That's it. If the image of phi is inside a smaller subset, then phi of this one should be equal to the other one. Okay. And this is, as I said, the most controversial condition. Apparently, this framework has been developed by Nash. He worked a lot on this. Some people were not happy with this condition and they changed it to other conditions, but they are less general. I don't have a feeling right now about what is the meaning. Probably in order to really understand, we should do examples. So I encourage you to play on examples and check. Probably you can find examples about this. Try to understand what is really the meaning of this condition. But yeah, it's the most controversial one and people have tried to change it. Okay, so now what? So we had these four conditions. So remember, phi is it's a recipe which sent any bargaining problem into one point in FD. Okay. So you can wonder, oh, now is there a phi which satisfies all this? Or maybe I can state it like this. The directly theorem, but I will be more precise later. I change the order. There exists a unique, but I will even construct it in a second. There exists a unique allocation rule phi from the set of all bargaining games to n, which satisfies the four conditions. So the condition E, E, F, the condition S, Y, M, the cat condition, and the I, A condition. So the statement, but again, I will be more precise, is that if you impose to phi to satisfy these four conditions, and if you're happy with these four conditions, then phi is unique. All right? Which is good. We like when there is uniqueness. And as I said, people also change these fourth condition, but it's less general. Okay. But we can do more than this. Okay. In fact, we even have this explicit phi. So in the notes, I start by exhibiting this phi or defining this phi, and then I state the result. So here I did it in the reverse order. So how do we define this phi? So for bargaining problem, so for FD, for bargaining problem, I'm going to set, I define a function G with the index D. It's a function from Rn to R, given by G index D of X is a product Xi minus D. So it's a product product I from 1 up to n of xi minus di. So you take this difference. So remember, d is in Rn, x is in Rn. So you have n components. You do xi minus di, and you do the product I from 1 up to n. So it means the good point is that this function g d of x is bigger or equal to 0 for any x inside fd. Because remember, this set fd is made of points which are bigger than d in this precise sense introduced. So it means all these factors here are bigger than or equal to 0. Oh, so it's a function which is positive on fd. We are happy. And it represents, let me just write what it represents. This function, it represents the product, because it's a product, the product of the gains of the players compared to or with respect to the disagreement point, because it's a difference with the disagreement point. Okay, so we have an interpretation of this product. If we think that this difference is what player I can get compared to the disagreement point, it's a positive number, then it's a product of these gain, or the product of these, what each player can get. Now, exercise for all of you. Show that this function admits a unique maximum on fd. And yeah, think about this. Here the shape of fd is going to play a role. It's not true for an arbitrary set, but we have condition on f. fd is constructed from f. So you have, as I said, you need to draw some examples. What means this convex hull, or what is these comprehensive sets? Okay, you need to do this, right? Oh, but once you know that there exists a unique maximum on fd, so let me keep this. So I define this function. This function, be careful, it's well defined for all bargaining problem. In the first definition of GD, you don't see the set F. You only see this point D. But in this exercise, you see the set F, because the statement is that there exists a unique maximum of this function in the set FD. Okay, so if you have a uniqueness, of course, you need a definition for any bargaining problem of FD. I emphasized, but I do not need set NA. It's probably for N is probably for Nash. NA of FD is, okay, let me use this argmax on FD of GD. What does it mean? It's exactly this unique point. And it means this is only one point. So this NA of FD is the point in FD where the function takes its maximum. And this is called the Nash solution. And now I can finish this theorem. I said there exists a unique phi satisfying these four conditions. Phi is given by NA. It's meaningful because look, NA takes any bargaining problem and send it to a unique point. I should emphasize this is unique allocation in Rn. It's unique because of this exercise. So it means NA associate to any bargaining problem a unique point in Rn, and this is exactly what phi does. And the statement is that this phi given by NA satisfies these four conditions, right? And there is you can find in the reference book or in other places, there is a statement which says that you cannot remove any of these four conditions. If you remove any of them, then you lose the uniqueness. So it means you really need these four conditions. They are necessary and sufficient. And as I said, some people were not happy with the fourth condition. They look for alternative condition, but as far as I could see, it's less general, or you cannot do it for arbitrary numbers of players. I encourage you to Google this subject and to look at some examples. I didn't do bargaining problems, but I'm confident that you can find something. Look at an example, draw some pictures just to understand what is going on. As I said when I started with this second section, these bargaining problems are quite simple because at the beginning I mentioned these coalitions. Here you see there is no coalition. All players are in fact, they are playing all together because we look at this, there is no subset of S, we take all of them together. The next section will have a more structure, but still it's good to start with this first example. Okay, that's all for today, and I hope you enjoyed. It's very annoying to speak in front of an empty room, so I'm looking forward to meeting you again at the very beginning of July. If you have any question, you can send me an email. I will respond to email. I cannot promise that I will correct any reports in the coming 2 weeks because I'm doing some research with some collaborators, but I will correct all your reports as soon as I'm back, and I hope you will produce many reports. Okay, that's all for today. Goodbye, and goodbye here.